morning, friends and dear students. I feel immense pleasure to be here again for my course, Flight Mechanics. I am in the process of discussing cruise flight. As of now, I have discussed different topics like phases of the flight, atmosphere, variation of density, altitude, temperature, different layers of atmosphere, thrust required, power required, thrust available, power required, power available, different velocities, stall velocity, maximum velocity, minimum drag velocity, minimum velocity for the endurance, minimum velocity for the maximum range, condition for CL by CD maximum, CL maximum at under root CD naught by K we have derived, total CD is equal to 4 CD naught. These all things we have already derived and discussed. We have also discussed the speed stability just before this class. In today's class, I am going to discuss about engine types with cruise flight. So here I am Dr. Yagya Dutta Dwivedhi, professor from Institute of Aeronautical Engineering, Hyderabad. I am from Department of Aeronautical Engineering, Institute of Aeronautical Engineering, Hyderabad. Today I am going to take these topics. First one is the straight and the level flight. Then engine types, performance criteria are also discussed. Fundamental equations, velocity and angle of attack relationship, and the numerical. This I am going to discuss in today's lecture. Revision of the last class, I have discussed about minimum drag speed, regions for the minimum drag speed, formulation for minimum drag speed, and speed stability. So we have just, I will draw a small revision here. So if I draw a tangent from here, this point, and if I draw a tangent from here, this is the minimum drag velocity and this is the velocity for maximum range, and this is the velocity for maximum endurance. That we have to take care. So minimum drag speed is very important, and this is called the minimum drag speed where you have the maximum endurance. Formulation we have already done for the drag speed, and it's the speed stability we have already checked that if your aircraft is like this. So this is the point 1 and here you have the point 2. If your aircraft is flying from here to here, this is in the stable speed zone, and if you are flying here, this is unstable speed zone. If you are flying somewhere here and here, you are likely to reach to the stall condition, V stall, and if you are here, you will reach to the maximum velocity. Your tendency is to reach to maximum velocity. So that is the difference between these two. We should not try in this zone because it is risky and sometimes during landing and all it may create some problem. So like this we have to take care of for the situation, and this we have covered in our last lecture. Now we will discuss about straight and level flight, some background on that. We have the jet aircraft. So phases of the flight, if you see of the jet aircraft, it is from here it is the taking off, from here to here it is a climb phase. If you see angle of attack is high, from here to here it is a cruise flight. Your aircraft is the same height, it is not changing, no rolling, no pitching, only straight and the level flight is going. As and when it is reaching to the destination, before that it starts descending like this. Angle of attack will be reduced, nose will be down, and then it will reach to the runway and the aircraft will land. So this is the straight and the level flight which is described here. A civil aircraft is in cruising flight for much of the duration of its flight. If you see here, nearly 80 to 90% of the flight is the cruise flight. Cruise flight is a major part of an airplane mission and is defined as the straight line flight where the velocity and altitude are often kept almost constant. So V is constant and rho is constant. Means altitude. Rho is what? Altitude means height. So height is also constant. There will be no climbing and descending in cruising. There will be no climbing and descending in cruising flight. Types of engine used in a airplane. Aircraft engines are classified into two main groups. One is the propeller driven engine, that is piston prop, turboprop. So here it may be the piston prop or turboprop. So if you see here, this is the IC engine. Here we will have the gearbox. After the gearbox, we will have the propeller. This is rotating and this is the gearbox. So there will be some efficiency term eta is. Here we have the piston engine. We also have the gas turbine engine also. In that also we need some gearbox, and after the gearbox, the propeller. This is the gearbox. This is the turbo prop. It is called turboprop engine. So any propeller driven engine, whether it is a piston propeller or the turbo propeller, and another is the jet engine. In jet engine, we can see that here it is the inlet. Then we have some compressors are there. They are the compressors. Then we have here combustion chamber. Then here we have some turbines. And here we have the nozzle. These are the turbines. This is the compressor. This is the combustion chamber. This is the inlet. So here we are not putting any propeller, but it is due to the Newton's third law, action and the reaction. Jet is going very fast and your thrust is produced. So jet engine is called the thrust producing engine. Thrust producing engine, and they are called the power producing engine. So this is the basic difference between these two. So I will just rub it up. So the main difference is that the output of a jet engine is thrust, that is called the T, and while the output of a propeller engine is a power, P. But the power is converted to thrust by the propeller. So this power is converted to the thrust by help of the propeller. Conceptual design of major component of the powered aircraft such as wing and the horizontal tail is based on the satisfying the requirement in this flight phase. So it's very important to study. So this your aircraft wing, your body, your all the parameters are very much important to understand about this. So we are going to study about this topic. 3 assumptions are made to make the derivation of the equations easier. Here we will make that the zero lift drag coefficient CD naught is assumed as a constant. Drag force D variation versus velocity is fitted, modeled with a parabolic curve. The induced drag correction factor K in the drag polar CD is equal to CD naught plus KCL square is assumed to be constant in the subsonic flight. So these are the parameters which we are to consider. So performance criteria, we have to see the specific speed in straight and the level flight. So what is the meaning of specific speed in straight and level flight? These are the criteria which we have to understand. That is, first one is specific speed in straight and the level flight. The second one is a range, then endurance, ceiling. So the specific speed. So first we will, I think something we have already discussed. Again, I am just revisiting here. The specific speed is the straight line level flight include maximum speed, cruising speed, minimum drag speed, maximum range speed, speed for absolute ceiling, maximum endurance speed. These are the speeds, and I think most of the things I have already discussed, but again I will revisit here. This is the TR, this is the velocity, this is the, so this is your T available. So maximum speed. So maximum speed is the speed when TA is equal to TR. So this is the speed here. If I drop here a perpendicular, you will get here V maximum here. This is the maximum speed. Any aircraft cannot go more than this speed. Cruising speed, if you see here, cruising speed where the range is maximum. Okay, so the speed when lift is equal to drag, lift is equal to weight, thrust is equal to drag. This speed means L is equal to W is equal to half rho V square SCL. So V is equal to under root 2W by S rho CL. This is the cruise speed. This is the cruise speed. Minimum drag speed is the speed at this point where TR is minimum. This is the V minimum drag. Maximum range speed, if we drop a tangent in this, so you will see that this point where it is touching, this point is a V max range speed. Absolute for ceiling, absolute ceiling speed. When TA is equal to TR, aircraft cannot go beyond this called absolute ceiling. Maximum endurance speed, speed at which drag is minimum. So V minimum drag. So it is 0.1, 2, 3. So it is a 0.1. Okay. So these all points I have discussed here, and hope you have understood these all things. Now I will discuss about some fundamental equations. Steady state trim equation. Newton's second law, which states that when a net external force sigma F acts on an object of mass m, the linear acceleration A that results in is directly proportional to the net force and has a magnitude that is inversely proportional to the mass. The direction of the acceleration is the same as the direction of the net applied force. In equation form, we can write that sigma F is equal to ma. The external forces that include aircraft weight, engine thrust, drag, and the lift. So this we can see here in the this diagram how these things are happening. So in x direction, here it is x direction means in the longitudinal, y means in the right wing. This is the right wing. Right wing is positive, and z is below is positive, and x forward is positive. So sigma fx is equal to max, sigma fy is equal to 0, sigma fz is equal to 0, because we are assuming that forces are not acting in this y and z direction. In cruising flight, we do not consider any turning motion and the side force, so we ignore the y component equation of motion, and then the equations are reduced to two equations, that is sigma fx is equal to 0 and sigma fz is equal to 0. These 5 and 6 equations are for accelerated flight. Fourth equation, the straight line level flight is often unaccelerated, that is constant cruising flight. The equations are simplified as follows: sigma fx is equal to 0, sigma fz is equal to 0. These two equations. These equations demonstrate the force equation of motion. The basic equation of motion that governs the straight line flights are as follows. This is for the cruise flight. That is, if I make the aircraft like this, these are the wing, this is the tail, this is the lift, and this is the weight, this is the drag, and this is the thrust. So equation 1 and equation 2. So we can write that thrust is equal to half rho v square s cd, and this weight is equal to mass into gravity, and this is half rho v square s into cl. So here the location of your cl, l, and the w are not in the same way. The drag and the thrust are not in the same direction. So there will be a couple between these forces. So trim equation: an aircraft has low angle of attack less than 5 degrees during cruise flight and has a low engine setting angle, that is the trim equation in a cruise flight. Or this you can see here, that in this diagram, that d here, d is equal to t cos alpha plus it, ie here, this angle, and this w is equal to l plus t sine alpha plus ie. Ie is a setting angle, where alpha is the aircraft angle of attack, that is the engine, and ie is the engine setting angle. So these are the equation of motion for this case. Now we will discuss one numerical for this. A jet transport aircraft with a mass of 120,000 kg is cruising with a speed of 400 knot at sea level. If the drag force is 290,000 Newton, the aircraft angle of attack is 3 degree and the engine setting angle is 4 degree. How much thrust the engine is producing? How much lift force the aircraft is producing? So we have to find out the thrust, we have to find out the lift, and we know the equation here. D is equal to T cos alpha plus IE and W is equal to L plus T sin alpha plus IE. So we want to find out this and we want to find out this. So here we can write that L is equal to W minus T sin alpha plus IE and T is equal to D minus D by cos alpha plus IE. So we have to use these two equations and solve this problem. So here you see that D is equal to T cos alpha plus IE as I already told. So here T is equal to D by cos alpha plus IE. So it is D is 290,000 divided by cos, 3 is angle of attack and 4 is the setting angle. So if you take this, we will get 292 177.8 Newton. So this is the thrust of the engine is 292,177.8 Newton. Same way we can find out the lift, and we have seen just now the equation for this. W is equal to L plus T sin alpha plus IE. So L is equal to here W minus T sin alpha plus IE. W, you put this value of W, you will T we have to find out from here, and then you will get this is the lift. So this is the lift is equal to this much Newton. Now we will see some further detail about different points on the TV diagram, thrust and the velocity diagram, drag, thrust and the velocity relationship. Some points we have already discussed and some point we are going to discuss just now. There are low engine thrust required, such as T1, not enough for cruising flight. So if this TR is less than this some value, your aircraft, this you can see T1, if your aircraft has got this much thrust, it cannot fly the aircraft. Okay, at any thrust that is less than the maximum and more than the T2. So T max and it between T max and T2, the thrust line has two intersections with the drag curve. This means that the aircraft may have two cruising velocity at such particular thrust. So it may have two velocity. If you can see, one is here, one is here. So these are the two velocities which aircraft can cruise. The thrust T2 is a minimum thrust. Thrust T2 is a minimum thrust where cruising flight is possible. This velocity is referred to as a minimum drag velocity. So this velocity is called the minimum here, minimum drag velocity. If the pilot employs the maximum engine thrust T maximum at any particular altitude, the aircraft will have its maximum velocity at that particular altitude. So if it is applying the maximum thrust, so at that altitude it will go for the maximum velocity of that altitude. Again, one numerical, we have more numerical, it is there. An aircraft with a mass of 2500 kg, a wing area of 18 meter square and a drag coefficient of 0.04 is cruising with a speed of 160 knot at a constant altitude. If the pilot increases the engine thrust by 20%, calculate the initial acceleration and the final velocity. You may assume the drag coefficient is a constant throughout this flight and the aircraft is flying at international standard atmosphere condition and sea level. Very interesting. So here mass is given, area is given, drag coefficient is given, speed of the aircraft is given. If the pilot increases the engine thrust by 20%, calculate the initial acceleration and the final velocity. Okay, so this we'll see here. In a cruising flight with a constant altitude, the thrust is equal to the drag, while the drag is equal to the half rho v square SCD. Thus, T1 is equal to Di is equal to half rho v square SCD. Half rho is 1.225 v square 160 into 0.5144. To convert from knots to meter, we have to multiply by 0.5144 v square. Area S into CD is given 0.04. So we got the thrust is equal to 2987.3 Newton. So when the engine thrust is increased by 20%. So now if we increase this, so T2 minus Di is equal to MA. So A is equal to T minus Di by M. So this T is increased to 20%. So 1.2 into 2987.3 minus 2987.3 divided by 2500. So acceleration will be 0.239 meter per second square. So we got the acceleration here. This acceleration will increase the aircraft velocity until the drag is equivalent to the thrust. So now T2 will be is equal to D2 is equal to 1.2 T1. So half rho V2 square S CD. So V2 is equal to 1.2 T1 divided by half rho S CD. So V2 we will get here 90.1416 divided by 0.5144. We will get this knots. The ratio between the new speed and the previous speed is 175.22 divided by 160. It is 1.1. It means that aircraft velocity is increased by 10%, although the thrust is increased by 20%. So we have increased the thrust by 20%, but velocity has increased by 10% only. So very interesting result here. We can do some analysis part of this. Students should feel the physics of that, not the numbers, not the mathematics, but see the result that after 20% of thrust increase means you are putting 20% of the fuel, but you are getting only 10% of the velocity. So you should not go very much high speed, otherwise your fuel consumption will be very high, but your result will not be good. So that we have to take care of during our any type of flying or any type of activities. Now we will discuss about velocity and angle of attack relationship. What is the relation between the velocity and the angle of attack? And we can see here some plot here, CL versus velocity. As you increase the velocity, your CL will decrease. You see the birds. When the birds are landing, they need more CL, but velocity is less. So they are inversely proportional to each other, and we can also see that L is equal to half rho V square S CL, or CL is equal to lift divided by half rho V square S. So if you take this, CL is 1 by V square. Parabolic function. It is in the decreasing order. So if velocity is increasing here, velocity is increasing, your CL is decreasing, and vice versa. Same way, if you see the angle of attack here, angle of attack and the velocity. So here also your CL is directly proportional to alpha, but alpha is inversely proportional to V square. So here also you will get the same type of pattern for the alpha and the velocity. So this is also very important. Every student should understand this concept because so much confusion is there. People will see that if the velocity is more, your CL will be more. It is not so. Your CL and angle of attack is directly related, but velocity is inversely proportional to the coefficient of lift and the angle of attack. Typical variation of lift coefficient and angle of attack versus velocity in a cruising flight, it is shown here and it is giving very good results. Representation of velocity and angle of attack relationship. So if you see here that it is 220 knots your aircraft is flying, here the angle of attack is 3, but if you reduce the velocity, your angle of attack is increased. Velocity high, velocity low. So it is opposite. So one aircraft in two different cruising flight condition, that is at V is equal to 220, angle of attack is 3 degree. V is equal to 120, angle of attack is 60. So as you decrease the cruise speed, you have to increase the angle of attack. As you increase the cruise velocity, angle of attack you have to decrease. Here we have some two aircrafts. Here this is the F-35. Comparison between angle of attack of a high-speed aircraft that is F-35 Lightning to left, and a low-speed aircraft P-35 Lightning right. So the high speed will have the angle more, and at the low speed your angle is reduced. So this, how to see that here, and it is a angle of attack is more to get the same CL, and here it is alpha is less, and here alpha is. Next lecture I am going to discuss about point mass model, modeling of CL. Okay, these all things I have already covered. So my references are Anderson JD Junior, Aircraft Performance and Design, International Edition, McGraw-Hill's first edition, 1999. SL by ME, Aircraft Performance Theory and Practices, AIA Education Series. Any questions you are welcome to ask. I would also request you people to like and subscribe my channel. Give me the motivation for that. If you feel anywhere some improvement is required, some mistakes are there, please do write in my comment box, or you can send mail to my yddwivedhi@gmail.com. This is my email. You can send a mail to me in this mail. Thank you very much. Soon I will be taking some very interesting topics. I will cover some numericals on atmosphere. I will also cover some gate examinations, previous question paper related to the flight mechanics. I will take some 3 to 4 lectures very soon. So it will be very nice if you are attending and you are trying to attempt for flight mechanics. It will be quite good. Till then, see you. Goodbye.
Like, share and subscribe. Hit the bell icon for more updates.